Recording.
Talk.
Thank you. Thank you, ma'am. Are you? Hungry. Okay, okay, guys, so can you guys hear me? See if I myself.
Yes, also from remote.
Okay. So before we start, a small logistical announcement. So one of the things that I've suggested is a slight change in the schedule. So rather than finishing at 3:30, we'll finish in 2 to 2:30 today, and we'll have the homework session after Tarawih. online in Zoom. Okay, same link. The reason for this is because it's Ramadan. Last week I was observing the energy was extremely low in the last 1 hour. And the homework sessions are important. The hands-on session, I'm sorry, are important. I want you guys to be more engaged in it. So I would suggest we start around 9:45 to 10 p.m. in the night and go for about 1.5 to 2 hours, as long as it takes to see the practical implementation of the tools that we are studying in the class. Okay. I will ask Shai or one student to share the Zoom link in the group. It will be the same Zoom, so no need to have another one. And Ali, Doa, and the other TAs will lead the hands-on session. I'll join in to see that everything is in order, and then leave you guys in the capable hand of the teaching assistants. Okay. So morning, from 11 to 2:30, we'll have lecture, cover the topics, and the hands-on session for Ramadan would be in the evening. I would suggest 9:45. I'm quite sure Taraweeh is finished by that time for all of you, right? Okay, so let's do 9:45. Okay. Okay. So if one of the thing is that I have kept my speaker on today because we have a couple of faculty members from KAUST who are attending the lecture, and I want them the ability to ask questions if they want. So you would have to mute your microphones. If you are attending Zoom from the class, mute your microphone so that we don't hear the echo. Okay. So essentially, the agenda for today is to have a review of what we did last week, just so that we are on top of all the concepts that we have covered so far. Look at transformers in detail, okay, and then look at the application of transformers for large language model, i.e. what are these LLMs, which are transformer-based architectures, how are they trained, what are the essential components for their training, and then how are they deployed at test time? How do we use them for chatbots, for sentence completion, for summarization, for application across different domains? Okay, that's the overall agenda for today. The next 2 days, we will look at reinforcement learning with human feedback, which is one of the most essential component of training large language models. So I would say if you pick up a random paper of state-of-the-art large language model, about a third or a fourth of it would be about reinforcement learning with human feedback. That's what made large language models possible. It's a slightly tangential topic to core NLP because it's very recent. So reinforcement learning with human feedback started in the field of natural language processing with GPT-based architectures. Before that, people weren't using RL-based algorithms in NLP, but it has become very important. So we will look at it over the next 2 lectures. And the last lecture, we will just broadly look at some state-of-the-art applications of large language models. Okay. So to start off, let me set up the challenge for you guys, what we are trying to solve. Essentially, we have on the internet a large amount of text. Okay, so we have English language. Okay, we have different sentence, articles, stories of English language on the internet. And the target for us is to learn a distribution from which I can sample this text. So I want a distribution on English language. Okay, that's the target. Yes. Okay. How about now? I think it might be the configuration of the speakers. But is it like, is the audio low or is it not clear? Echo, okay. Let me try without the microphone and see if it's better. If it's not, I will turn the microphone back on. Okay. How about now? Is it better than the previous one or not? The previous one is better. Okay. Okay. So I'll try to do my best to speak a bit louder. Hopefully that would allow us to speak through the echo. Okay. So this is the problem. Essentially, I want a distribution on English language. I want, if I have a probability distribution of English language, if I sample from it, it will give me real looking text. Alternatively speaking, if I have some text, I can see what is the probability assigned to that text by this probability distribution. And then I can say, hey, this is a real looking text, or this is an unreal looking text. The problem is that this is not an easy task. It's a very difficult task to have a distribution on English language, and then you sample from this distribution and you get sentences and text. Okay. So what did we do? How did we try to break this problem into something that we can solve? Okay, remember the task was language modeling. Okay, I want to have a model for language. What I have currently is just large amount of samples from this distribution. I don't have access to this distribution. Can I learn something which is a stand-in for this distribution, a distribution which is, let's say, in some sense close to the unknown distribution of English language? What did we do? What was the first step that we did? Okay, so Hamid is saying predict the next token, but you are jumping a step or two further. Okay, this predicting the next token came. Essentially, you have data, right? Now you know that this data comes from a distribution. You don't have that distribution. What can you do with this data to go close to the distribution that you don't know? Remember, we talked about likelihoods. Okay, what if I like a distribution, a parameterized distribution, and then try to write the likelihood of the data that I have observed through that parameterized probability distribution? Okay, this I can do. Okay, nothing is stopping me from doing that. So what I will say is that, hey, I will have a distribution parameterized by theta. Okay, I will write it as some functions of theta. Okay, and then I'll try to write how likely it is to observe this data through p theta of x. Okay. This I can do. Of course, I would need some simplifying assumptions to write the likelihood of my data, but we can do that. Okay, so what I did was I said that, okay, the first thing that I would do is that all these samples, I1, 2, 3, all the way till n, you can think of them as sentences, you can think of them as articles, you can think pieces of text information on the internet. I would assume that they are IID. Okay, they are independent and identically distributed. That's the first thing that I would do. Okay, in this case, it's a reasonable assumption, because if you are looking at two separate articles on the internet, the probability of them being related to each other is virtually zero. Okay, they would be independent of each other. Okay, they are identically distributed because I have mentioned that all the samples are coming from this underlying distribution p theta. Okay, so what I can do is I can write this total distribution of the joint distribution of this data, my data set. I can write it as product from I equal to 1 to n, probability, the product of probability assigned to each piece of information. Okay, each piece of text. This is the first simplifying assumption that we did. Okay, and what made it possible for us to write it? It's the IID assumption. Okay, so now we are going somewhere. First step is done. Now the second challenge that we have is that the data that we have, the text that we have, this is not fixed length. Some of the sentences might be 2 words, some of the sentence might be 3 words, some of the sentence might be 4 words. Okay, so it would be very difficult to write a distribution in a d-dimensional space for this data, because this d is not fixed. Okay, some sentences are 5 words, some are 10 words, some are 20 words, some are 100 words, and so on. So what did we do for that? What did we do to solve this problem? So again, the challenge is that each of these sentences, xi, they are different length. Okay, some of them are 2 words, some of them are 3 words, 4 words, 5 words. Remember, when we are writing the likelihood, for example, for classification problem in images, all the images are essentially same size, or we resize them to same size, and the classification space is the same size as well. We have n classes, and we are just classifying them, the image, into n classes. Text is slightly trickier. Text is slightly trickier because text is not fixed length. It's not fixed size. It can be any length. Okay, starting from 1 word to, I don't know, 1 million words or 1 billion words, or whatever you want to put as an upper limit. Okay. 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 So what Shah is suggesting is that we can fix a certain sentence size and then pad it. Okay, but can we do something better? So, because remember, what are we doing in our language models in NLP? How do we produce information? Because you see, you have to produce a text. You don't know what is the size of this text. So how do we produce that text? How? Exactly. So the way we break it down is we say that, okay, we will say that let's use some sort of Markov assumption in the beginning. Okay. So let's say that if you have a stream of text, okay, let me write it as x1, x2, all the way till some xm. Okay, I have to write a probability distribution for this text. Is it okay if I write it as probability of x1 times probability of x2 given x1 times probability of x3 given x2 and x1 all the way till probability of xm given xm minus 1 to x. Can I do that? So I'm just using iterative application of Bayes rule to write the joint probability as sum of as product of conditionals. Okay. So if I do this product, okay, using Bayes theorem, this would become probability of x2, x1. Okay. This thing would become probability of x3, x2, x1. And then you can iteratively apply it until you can say that this would indeed be probability of x1 to xn. Okay. So now I have simplified the task of language generation into a task of next token generation, conditioned on the previous token. Okay. This is the core simplifying assumption that allow us to do language modeling. Okay. Everybody is with me? Okay. All the language models that we currently have, it uses this assumption. So we are doing next token prediction on it. We have some text conditioned on this text, we predict the next token. Then we add this next token to the available text, condition on this text, we produce the next token. Then we add it to the available text and produce the next token. This is how Cloud is working. This is how GPT-4 is working. This is how Gemini is working. This is how Llama, Falcon, all these large language models, this is how they're working by producing the next token. Okay. So let me take this simplifying assumption and add it to our original likelihood expression that we're trying to write. Okay. So now my probability of observing the data or the likelihood of some data under the probability distribution parameterized by theta. This would be the product of n IID tokens of pieces of information, and then a product from j equal to 1 to, I would call it mi, because m can be different for different sentences. Okay, some sentences can have 5 words, some sentences can have 6 words, some sentences can have 10 words, and so on. And then probability of j x. Okay. Now this is something, this expression is something which I can essentially handle. So what do I have? I have a probability distribution on the next token, okay, for the length of all sentences, for all sentences in my database. Okay. This is the likelihood of observing your data under this parameterized distribution theta, under this parameterized distribution phi theta. Now what you can do is, as you do in all machine learning, once you write your likelihood in terms of some parameterized probability distribution theta, you can change the theta to make your data more likely. Okay. Essentially, the core idea is this: I have some data coming from a distribution which I don't know. However, I can write a parameterized distribution, phi theta, and I can change theta such that the data that I have observed becomes most likely. Okay, that's the best you can do. If by the way, this is what we do intuitively. If I tell you that, okay, you are flipping a coin and you flipped a coin, let's say 100 times, and 70% of the time you got ahead, what is the probability of ahead from it? You say, oh, the probability of ahead is 0.7. Okay. When you look at it under the hood, you are doing maximum likelihood. You're just maximizing the likelihood of seeing your data from this distribution, which is parameterized by theta. Okay. So I have set the problem of language model as a nice mathematical problem, as a nice optimization problem to be exact. But this doesn't seem like an easy function to optimize. Okay. So if I want to optimize it, if I want to maximize this likelihood, what would I do? Well, I can do the standard thing that we do in optimization. I can take the gradient, and in this case, take a step in the ascent direction because I want to maximize the probability. Okay. But it doesn't look like a trivially easy function to take the gradients of because we have too many products. Okay? In general, when you have products in an optimization function, try to somehow make them into sums. Okay? Sums would make your life easy. Okay. So what we typically do in this type of applications is we say rather than maximizing the likelihood, we will maximize the log likelihood. Okay. So remember, I'm interested in the parameter theta. I'm interested in the value where I get the optimum. I'm not interested in the value of the optimum. Okay. So any monotonic function which does not change the location of a maxima or a minima is fine. You can apply it. The location of the maxima and minima will not change. The value would change, but I'm not interested in the value. I'm interested in the values of the parameter theta. So what you do is you say, I will take the log likelihood and I will maximize the log likelihood of the data rather than maximizing the likelihood of the data. So let's see what this will do. So the log likelihood, the products would become sum. And you would have to have the log of. Now, this is something that looks very similar to typical cost functions as loss function in machine learning. Okay. For no good reason, rather than maximizing functions, we like to minimize function in general in optimization. So rather than maximizing the likelihood, is it okay if I minimize the negative log likelihood? Yes, I can do that. And now this thing should be familiar to you. So once you see this negative log of probability theta of xi, what does it look like? This looks like a cross entropy loss function. Okay. And now we are going somewhere. Essentially, what you want to do is you want, quote unquote, a deep neural network, which can give you a distribution on next token. Okay. If you can do it, then you add the cross entropy loss for all the next tokens in a sentence. You add these loss for all the sentences in your data set. Now you have a loss function which you can minimize. And we have the whole arsenal of artificial intelligence machine learning tools with which we minimize the loss functions. Okay. So essentially, I have apparently seemingly a very intractable problem. I have taken it and I have managed to write it into a way which I understand how to optimize, which is just set up a deep neural network, which gives you a distribution on next token. You take the cross entropy loss of the distribution of next token with, of course, the ground truth. And that's it. You are set. Okay. So let me try to take this mathematical formulation and write it into a machine learning formulation, which we understand. Okay. So what I would do is what I will have is I will have a deep neural network parameterized by theta. Okay. It would take some tokens. Okay. So I'll call it, let's say, xi -1, and it will give me a probability distribution on This I can do. This is typically a neural network or a deep neural network. We can do that. Okay. Then this is a distribution assigned by your deep neural network. You also have the ground truth. Okay. So let me take an example of a sentence. Let's say today's class is about transformers. So let's say I give this as input to the neural network, and I ask it to give me a distribution on the output words. Let's say I get an output distribution, which is, let's say I have okay, about music. So let's say music get a probability of 0.1. Okay, let's say I have art gets a probability of 0.2. Okay, NLP get a probability of 0.2. And then let's say transformers get a probability of 0.5. This is your output distribution from your neural network. Okay. One question, by the way, I just want to ensure that everybody is with me. How do we ensure that we get a probability distribution from output of our neural network? Softmax. So we use a softmax layer. Softmax layer would take in real numbers and convert these real numbers into a probability distribution with sum equal to 1. Okay, so the final layer of your neural network, of course, in this case is softmax. And now you have the ground truth as well. So the ground truth, I know that the ground truth is transformer. So what this cross entropy loss would translate to is essentially just take the probability of transformer which in this case is 0.5, take the negative log of it, and that's essentially your loss. Okay? You ignore all the other distribution, all the other probability values. You just look at the correct label, take the probability assigned to the correct label, take the log of it, multiply it with -1. These are things which we can do. Okay, I can go to the ground truth label in the output distribution of my neural network, see what is the value assigned to it, take the log of it, multiply it with -1. Okay, now I have a loss which I can try to minimize by changing the value of theta. Okay, as I mentioned, we'll take gradient, we'll take a step now in a gradient descent direction. Okay, all of this you don't need to worry about too much because backpropagation or deep learning libraries take care of it for us. All we need to do is set up the forward problem, which is going from data to the output distribution and setting a loss on top of this output distribution, and we are set. Everything in the backprop will be taken care for us. This is essentially language modeling. So we have set up problem for language modeling. Now, the challenge is, all you need to do is you need to give me a deep neural network, which can take in a sequence and give you output distribution on a vocabulary. Okay, I will fix a vocabulary. Let's say I'll make the problem easy for me. And I'll say that in the beginning, I want to do the prediction character by character. Okay, so I have a 26, my dictionary size is 26. I have to have a distribution from A to Z. I would take English language, I would remove punctuations, I would remove anything which is not English, and I will make it lowercase. Okay, so now I have to have a 26-way output distribution from my neural network. I can set it up, I can have a couple of layers. Output of my neural network is 26 dimensional. I put a softmax, now I have a distribution. Now the challenge that you guys have to help me solve is how do I have a variable length input to my neural network? Remember, you have a string of characters now, right? So you might be predicting the second character, or you might be predicting the 31st character. So if you are predicting 31st character, then 30 characters are input to this neural network. If you are predicting the 6th character, then 5 characters are input to this neural network. Okay, the neural network architectures that we have seen so far in this course, they take a fixed input, give you an output distribution on a fixed dimensional space. Okay, so far we do not have a mechanism of taking variable length sequence in the input and giving a variable length output distribution on the output. In this case, I don't need to worry about variable length output because I have broken my problem down as predicting just one token at a time. But input, I have to I have to figure out a way to solve it. Okay. So any guesses as to how I can solve it? We have seen, remember, we have seen statistical tools and grams and so on. We have looked at neural network based tools where we can do some sort of Markov assumptions. You can say that the next token depends on the 4 previous tokens. Then we looked at recurrent neural network, LSTMs and so on, which have a nice way of compressing information of all the previous token. And finally, we reached to transformers, which I will cover today. But so you guys have to tell me what are the possible things that I can do with this neural network. Let's start with let's say using Markov assumption and a fixed size neural network. So what can I do? So what is the Markov assumption? Okay, so what you can say is that, of course, it's for language, it's not a very strong assumption, but these are the first thing that people did. They said, okay, we are going to assume that the next token would depend on only 4 or 5 previous token. Or if you want to use the language of Markov assumption, you would say that given the 4 previous characters, the next character is independent of all the previous characters. Okay, so essentially, the Markov assumption would be that probability of xi j given xi j minus 1. Let's say I take 4 previous characters. This is equal to okay. So after you have seen the 4 characters, the 4 previous characters, all the other previous characters do not give you any more information about predicting the next character. This is a Markov assumption. And this is the first thing that people did when using machine learning, deep learning tools for language modeling. Okay. And what this turns out to do is that I take the same sentence that I have. Today's class is about transformer. Let's say I have this information and I want to predict the next token. So what I will do is I will take the previous 4 tokens. So in this case, it's space OUT. So I'll give it OUT space, and I'll ask it to predict the next word. So I'm interested in T. I'll put the loss or the probability of T outputted by your network. You will sample from this distribution. Okay. The next thing would be U T space T. Then you ask it to predict R and so on. Now this is what, yes. Okay. Some of the screens, I think, okay. Okay, I think we're good now. But yeah, you have to prompt me if it goes away again. Okay. Yeah. Screen is not shared. It wasn't shared from the beginning, or it disappeared in the middle? Okay. Okay, please keep an eye on the Zoom as well. If the screen is not shared, just let me know, because I'm recording it. It's good to have the screen recorded there as well. Okay. So now we have set up a seemingly intractable problem into a problem that we can handle very well. And that's basically the first attempts of using machine learning tools for language modeling. Okay. Of course, we know that language is slightly tricky. You cannot typically say that, hey, the next word depends on only previous 3 words or previous 4 words or previous 5 words and so on. You can have cases where the context length, very large context length, is required to predict the next word. So the next iteration of language modeling tools try to overcome this problem using a set of tools called recurrent neural networks. Okay. So the next iteration, this is the first iteration, which is neural network with Markov assumption. Now we have recurrent neural networks. So what did we do in recurrent neural networks? What was the idea? Okay, but this is we are already doing that, right? We are trying to write text as a time series, as a sequence of information which is coming with time. So it's not something unique to recurrent neural network. What was the core idea of recurrent neural network? History. Okay, the core idea of recurrent neural network was that, okay, the context length, the number of words that you need to predict the next word, it can be different. If you are, for example, predicting the second word in a sentence, you are looking at previous one word. If you are predicting the third one in a sentence, you are looking at previous two words, and so on. That's variable length. But can we find a way to compress all these previous tokens into some sort of history vector? Okay, so essentially the idea is this: you take in any length sentence. So for example, today's lecture is and you give me a fixed history size. Okay, a vector of fixed size, fixed dimensions, which captures all the history of my sequence so far. Okay, that's the core idea of recurrent neural networks. But what you guys should see is from the screen is that this is the same problem that I had for modeling length. If I can take any length sequence and give you a fixed vector, this is essentially the same problem as taking any length sequence and predicting a distribution on the next word. Okay. So what is the let's say the core understanding or the core concept in recurrent neural network which make this thing work? So remember, I'm trying to write the history of what I have seen so far. I'm not predicting anything from it. I'm just looking at some information and trying to compress it. Now, if I give you history at time t-1 and give you a token at time t, if let's say we have a perfect way of compressing information, you're not losing any information. History at time t-1 should be enough for all the characters or all the tokens that you have seen before time t-1, right? So there is an iterative nature to creating history vectors. So what we do is we say that we will do this. We will take any sequence. Today's lecture is about transformers. And we will say history at time 0 is just 0. We start with 0 vector. Then you have a deep neural network which takes a history at time 0 and it takes in the word at time 1. Okay, and it gives you history at time 1. Okay, now you take history at time 1 and you take word at time 2, feed it into this neural network, it will give you history at time 2, and you repeat this process. Now you look at your neural network. What is the input to your neural network? No, in general, what is your neural network taking? It's taking a history vector and it's taking in one token and it's giving you an output history vector. Now, this is a well-posed problem for neural networks because essentially it's taking two pieces of information and giving you one piece of information as an output. This was the core idea of recurrent neural networks. Okay, and essentially what we had was history at time t is some learnable function of history at time t-1 and x at time t, and you might want to have some output at each time step. This is optional, yt is optional. That's basically your recurrent neural network. Okay. Why is it called recurrent neural network? Because there is a recurrence in it. You are applying this history compression equation at each time step. So you'll take history at time 0, word at time 1, you'll pass it to your network, you'll get history at time 1. Then you'll do it again, until you Okay, you will repeat it until you get history at time t. Okay, so the typical architecture for recurrent neural network is basically some nonlinearity, typically a tan hyperbolic. Okay, and then y was, let's say that I have a binary classification problem, a sigmoid of first you have a bias term. Okay, this is your recurrent neural network equation. Okay, and now theoretically speaking, this should be able to capture an infinite length context. Okay, because you are iteratively squeezing in history out of any time sequence and then using it to produce y at each time step. Okay, what was the problem with this? Let me just draw this for you because visually it might be a bit better. So you have theta, h at time 0, x at time 1. You get output is h at time 1, feed in x at time 2, h at time 2, and so on. Okay, this is the rolled out recurrent neural network structure in time. I've rolled it out in time. Okay, now let's say I have some yt here and I have some loss on this yt. Important y hat. Okay. What was the issue that we faced with recurrent neural networks when we try to optimize these type of losses with theta? Vanishing and exploding gradient. So the issue is that when you're doing back propagation, okay, when you are taking the partial derivative of the loss function with respect to, let's say, ht minus 1, then going back in time, at each time step, you would have a multiplication with WHH. Okay. We can write the explicit equations, but we did them last week. So essentially, you would have the derivative of the nonlinearity with respect to input of the nonlinearity, and then the derivative of WHH ht minus 1 with respect to ht minus 1, which is iteratively applications of this multiplication with WHH matrix. So each time you go back in time, you incur a multiplication with WHH matrix. Of course, other things as well, but other things I'm not terribly interested in. In this particular case, I'm interested in what would be the effect of this iterative multiplications of WHH matrix. So let's say I'm looking at the partial derivative with respect to H1. It would have multiplications with WHH to the power t minus 1. Okay. That would be present. That would be a factor in your partial derivative of the loss function with respect to H1. Okay. And the issue is that if WHH has to be a very nice matrix for this number, this product to be bounded. So if, let's say, WHH has some eigenvalues which are, let's say, significantly bigger than 1, then for certain values, the iterative product of WHH would become very large. Okay. If WHH has some eigenvalues which are significantly smaller than 1 in magnitude, okay, what would happen is that for certain directions, the product of WHH would become extremely small. So this is called the problem of vanishing and exploding gradients. So typically, what happens is exploding gradients, by the way, are slightly easier to handle for us. How do we handle exploding gradients? We just clip it. So that if gradient is above value 10, take it as a max 10 and don't worry about it. Vanishing gradients are, however, slightly difficult to handle. So the issue is that if the gradients are vanishing, let's say that the gradient with respect to H1 is incredibly small, then what would happen is that this X1 would not be able to contribute anything significantly to this loss. Okay, because the change of this X1 would have very minimal effect on the loss. Why? Because the gradients are very small. So what this does is it restricts your context size. You're not able to look too far back in time. Okay, which essentially was the point of using recurrent neural networks. The whole point of using recurrent neural networks was so that you can look back in time. Okay, but now, because of this vanishing gradient problem, you cannot look too far back in time. You are restricted to a certain window. And typically, the window size is around 7 to 12 tokens, something like that. It cannot look too far back in time, which is not good. For language, it's not very good. So what did we do to solve this problem? So remember, vanishing gradient is not a new problem in neural networks. So you guys have seen computer vision. In computer vision, when we try to stack more than 10, 12, 15 layers, the gradients typically vanish and you are not able to train very deep neural networks for vision applications. What did we do? What was a nice trick that we used to overcome this vanishing gradient problems in computer vision applications? Skip connections. Okay, so what allowed us to go very deep in terms of architectures was residual networks. Residual networks have a skip connection. Okay, so essentially what we have is so in convolutional neural networks, what we have is a block, and then you allow a skip connection. Across some or all of the layers. This is a design choice that you use. So what the skip connection does is these allow a path for gradient to flow back. Okay. So now previously, if you did not have skip connection, there was only one path for the gradient to flow back through, which was through all these layers. Now with the skip connection, you have multiple paths for gradients to flow back. So if, for example, we were suffering through vanishing gradients here, this gradient flow was incredibly small, we have a path here for the gradient to flow back, and so on. Okay. Essentially, if you want to write it mathematically, this is f theta of x plus x. This would be a residual block. So if this gradient is low, you always have this where the gradient is just 1. So you can flow the gradient as far back into your network as possible. And residual networks work really well. You can go very deep. You can have 150 layers and so on. Okay. Now the question is, can I do something like this in language? Can I do skip connections in language? Now remember, why can I do skip connections in convolutional neural networks for vision application? Because in vision application, these layers, each layer has a semantic meaning. So earlier layers are looking at low-level features. Okay. Just a few pixels, 3 by 3 pixels typically. The next layers are looking at slightly larger regions, so slightly coarser features. The next layer are looking at slightly more coarser feature and more coarser feature and so on. So essentially what this skip connection is doing is it's providing a copy of the finer features and add it to the coarser feature, which is fine. So it's essentially, think of it like this, like at certain layer, your convolutional neural network is looking at very coarse features like this. Okay. The previous layer is looking at some finer feature, which is added by the skip connection. So maybe something like this. And the previous layer, which you added, it adds even more finer feature, something like this. So this is fine. In vision, we have a hierarchy of these features. We understand that there is a coarse level information, then there's a fine level information and so on, and you can just directly add them. But in language, it's not trivially easy to see which word is going to contribute to the next word. So for example, I'll give you an example. The sun, which is the lifeline of the solar system, is a medium-sized star. So the sun, for this part of the sentence, the sun is relevant, right? I would ideally want to have a skip connection to pass that information. Okay, but the same sentence can be also written like this. The sun is a medium-sized star. So now the skip connection is directly from here. So it's not trivially easy to provide these skip connections. So what we do in variants of recurrent neural networks, which are called GRUs or LSTM, is that we have a learned skip connection. So essentially, rather than having skip connections, which are just a simple addition of the input to the output, we have some gates. So we have some gated connections. And this gate can be open or closed, depending on what your data is. Okay. So essentially, and by the way, these are learned gates. So you learn these gates. So based on the current context of the sentence, it would see, hey, this word can become important, so it will keep it. It will keep that information until it's sure that this information is not relevant anymore. Then it will close the gate on it and not allow it to pass through time. Okay. So we looked at LSTMs, we looked at GRUs, and we saw that these were essentially the state of the art before 2020, before 2016, 2015, when attention came out. These were the state of the art. So the Siri on your phone, Google Translate, these auto completion, all of these were using LSTM-based architectures. Okay, and as I always like to say that the founder of the LSTM is Jürgen Schmidt-Huber. Is part of the faculty at CAST. Okay. I'm sorry? You have to repeat the question.
You explained this the problem with the input being variable.
Yes, yeah.
We still in the same issue.
Yes, we still have that issue, but it's slightly better. So remember, what was the context window for RNNs? It was 7 to 12 words, roughly speaking. So with LSTMs, with GRUs, we could go back and look at around 20 words. Okay, but we were not in the domain of having chatbots, because chatbots can literally require thousands of words of context. Okay, tens of thousands of words of context. We are not in that domain. Okay. So this problem, like the state of the art that we currently have, is transformers, and transformers is essentially based on attention. Okay. So now let's look at how do transformers work. What is special about transformers? So remember the first idea that we studied, where we said that we are going to use a Markovian assumption, and we are going to say that the next token depends on a fixed number of previous tokens. We came back to that. Okay. And we said that in transformers, we'll have a fixed context length. Okay. For example, for GPT-2 or 3, I think it was 32,000. Now we are more than 100,000. The context window that we use is more than 100,000 tokens. Okay. But it's fixed. Okay. The thing is, we say that we are going to look at such a large context window that most of the cases that we are interested in would be covered by it. So now we say that to predict a next token, we are going to look at, let's say I'll take the example of 32,000. All the way till previous words. But it's fixed. Okay, so as I keep on saying that it's good to see the history of the field of AI, because at times it's quite cyclical. We try to work with certain ideas, we pick some ideas, we work with them, we hit a wall, we drop them, we go to something else. Then somewhere down the line, somebody solves that wall problem and we come back. Okay. So this was, remember, the first idea that we said was that we are going to use a fixed size window and we are going to use a neural network. We couldn't make it work. We dropped it. We go to recurrent neural network, LSTMs. Somebody found attention. We came back to the original idea and said, now let's look at the fixed sized window. Okay. But it's not, strictly speaking, exactly like a neural network. So a neural network, if we were to use a fixed size window with a neural network, what would we do? We would take in J-1 all the way till, and we will predict. Okay. How is this different from attention? Remember, we saw attention last week. How is this different from attention of J minus 1. So attention, you can think of it as a very special type of neural network. Okay. But what is special about neural network? How is it different from a standard typical neural network that we have? So for a typical neural network, the weights are not a function of inputs. Okay. You train a neural network, you learned it. Now at test time, you have just some weights, fixed weights, you multiply it with inputs and you get an output. Attention provides you a mechanism of having flexible weights. Okay. Remember, what is attention? Attention is essentially the ability for a token in a sentence to attend to information of different tokens. So let's look at it. Okay, so let's say I have some x1, x2, all the way till xt. These are my t tokens. Okay, let's say my context size is t. Okay, the first thing is we get some embedding for these vectors. Embedding is essentially the information that is contained in these tokens. Okay, these are typically learned. Okay, you can use some fixed embeddings as well, but a transformer, these are typically learned. Okay. Now, if we had a typical neural network, what we would do is we would feed in these embeddings. And we would have some fixed weights. Okay. The weights for first layer would have been W1. We would have multiplied the weights with the embedding values, got the output, put it to the next layer, put it to the next layer, put it to the next layer, and so on. Okay. But what attention does differently is attention says that, hey, I'm not blindly looking at different tokens. What I'm going to do is when I'm at time t, I'm going to, based on the information that I currently have in this embedding, I'm going to collect useful information from all the previous tokens. Okay, so I have some information here. Based on that, I will attend to all the previous embeddings and try to collect useful information. Okay. How would we define what is useful? How would we define how we would attend to other tokens? So essentially what you have in this case is just vectors, right? You have a vector for xt and you have a vector for all the previous tokens. You have to somehow use these vectors to have a flexible ability to collect different information from different tokens. Okay. I might have mentioned it multiple times in this class, but the entire field of artificial intelligence and machine learning is just dot products. Okay. Just projection of vectors onto other vectors. Okay. So can you think of some operations of dot products for me to use the information xt to collect relevant information from all the previous tokens and add it to the information at time t? So I'm giving you a very complex task because we've already done it last week, but let's see how you can do it. Yeah. Okay. 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 So as a starting point, what I'm going to say is that a token would be relevant if it's similar to the current token if its embedding is similar to the current token at time t. Okay. So I'm going to take the embedding at time t. Okay. I'm going to take its dot product with embedding at other time. Let me write it with small t. Okay. This is going to be a proxy for how important a previous token is to current token. Okay. So now I have an important score. I know how important embedding at time 1 is. I know how important embedding at time 2 is. I know how important embedding at time t minus 1 is. Now, how do you suggest I collect information from all these embeddings and pass that information to embedding at time t? So I have real numbers, right? These dot products would be real numbers. Somehow, I would like my output embedding to be bounded in some sense. So I want a weighted sum, but I don't want these weights to sum up to an unbounded number. Okay, so is there a way for me to restrict the sum of these weights to 1, let's say? So it's a weighted sum where I take some fraction of all the previous embeddings, but these fractions add up to 1. How can I do that? Softmax. Okay, so what I will do is I will say that the importance would be the softmax of the dot product of the embedding at time t with embedding at time small t, where small t is from 1 to t minus 1. So t is from 1 to t minus 1. So now this tells me the importance. Now I need to, of course, pass the information from all the previous time steps to the time step at t, and the information that needs to be passed, the information from t to t would essentially be softmax of embedding at time t with embedding at time small t multiplied with the value of the embedding at time t. That's it. Okay, that's the information that is passed from time small t to time capital T. Now this is different from a neural network. Remember, neural network does not allow you this flexibility of passing of information based on the input. It only depends on the weights. The weights are fixed. Here, the weights are flexible. The weights are changing with respect to inputs. That's why attention is a much stronger tool than a neural network. Okay, and that's basically the key intuition. This simple thing made large language models possible. Yes.
So how each was related by
Exactly. Okay. Of course, this is, I would call it a very naive implementation of attention. Okay. We have very refined and smarter applications of attention, but I will motivate them in a bit. Okay. This essentially, think of it like this, based on the embedding, based on what your word is currently representing in its embedding vector, you are trying to see which other parts of the sentence are important to it using the dot product. When you have the values of importance, you pass the information from these previous tokens onto this current token using just a weighted sum of this importance. That's attention. That's basically the billion-dollar idea which made OpenAI and DeepSeek and Mistral and Gemini and Llama and all these models possible. Okay, not a super fancy idea, but it works, and it works really well. Okay. So what time is Zohar? Okay, so let's take a break, around 30 minutes break. Let's play Zohar and come back. We will motivate it a little bit more. We will see what are the drawbacks of this version of attention, how we can improve it, and how we can then subsequently build transformers and large language models on top of this attention implementation. Okay, thank you very much, guys. Guys, Shabab, the Giga, do you guys want some extra time for homework 1? Because I'm in no hurry, I can go all the way till the end of the semester. I can give you another week or another 2 weeks to solve the homeworks if you guys want it. Okay, so what I'm going to do is work on this homework. I will give you a single deadline for both homeworks, for homework 1 and homework 2, and I'll give you more than enough time because I want you to talk to Ali, Doa, Majid, and Mushtaba, and try to get their help to solve the homeworks, because homeworks are hands-on. I want you to get familiar with the training large language models, fine-tuning it, and so on, which will become very relevant in this. So you don't have to submit till Sunday. I'll extend the deadline for you, but make use of the peers. Drop them an email and say like, hey, I'm stuck here. My results are not very good. Can we improve it and so on? Okay.
So
So I don't expect super crunchy result, but some of them I ran. The result was like, okay. So can you share your books with me or with Ali? And we will have a look and we can suggest to you that, okay, this is good enough. Yeah, so we might suggest like a change this in that. Thank you.
Because for image capture, it's slightly good. For image generation, it's generated, but it's not consistent, or the context is very bad. We have put
Okay. Let me have a look. Let me have a look at your things.
I expected that because it's outdated techniques. Especially
Yeah, so I am just to let you guys see what Arik did. These weeks are like very modern. But like I said, it's good to know because, for example, now we have state space models, which are the Mamba and these kind of things. These are built on top of our.
Yes, I agree with you. The history is very, I agree also that the count that some of the new big schools, the buildings of some of the big schools, I agree. I mean,
It's fine. If it's reasonable, it's fine. As long as like we have standards. No, of course. But the whole point of it is to challenge you. Physics and applications class, I want you to like it. I could very easily get it better. But I don't think you guys are fine. More useful. Actually, that's why it takes, by the way, lots of effort to create these homeworks.
yes.
Because it's like we don't have like enough sources to find something which we can work on small resources and we can work it together. Yeah, but you sent a request? Can you resubmit it? Resubmit it to Sultan and I will, because it comes to me as well. Okay, when you submit an IB, I will say first, you come to me, not IB. I'll do it today. To do it today and I will. Okay. But to say Sultan Barakat. Sultan Barakat, yes. I'm a delegate, it comes to me as well. Okay. Okay, Assalamu alaikum. Guys, can we settle down? Can somebody drop a message on the group that we are starting? Okay, guys, let's settle down. Let's start. Thank you. Okay. Can you check that the screen is shared on Zoom? Okay, guys. Okay, settle down, everyone. Okay, Shabab, gentlemen, guys, can I have your attention? Thank you very much. Thank you. Okay, guys, so let's start. So far, what we did was we looked at the core problem that we are trying to solve, i.e. the problem of language modeling, which is trying to produce a big probability distribution from which if we sample, we would get real looking language or text. Okay. We saw how to cast this problem as a mathematical problem, i.e. we cast it as a maximum likelihood problem. And then we looked at the evolution of the field around it. So the first thing that we did was we said we will use fixed context windows for something like neural networks. Okay. There were some limitations of that approach. The next approach was recurrent neural networks. we did recurrent neural networks, which can, in theory, look at any context length. But because of some training constraints, we were limited to about maximum in its best iteration 15 to 20 words. Then we finally came to attention. Okay, attention is in some sense reversion back to the old state of the art, which is fixed context window. But in attention, we could do two things. One is we can typically look at slightly larger windows. So as I mentioned, early versions of GPT had around 32,000 tokens context window. The newer versions have more than 100,000 token size. Roughly speaking, it's more than a Harry Potter book. So the full Harry Potter book can be in the context of a token. Okay, we looked at attention, a very naive version of attention using the embeddings. So what essentially happens is that each token has its embedding. Okay, I'm noting it with E sub I. So if, for example, the token at time t wants to attend to the previous tokens from time 1 to t minus 1 and collect useful information from it, the way it would be done would be that we would get the dot product of the embedding of the token at time t with all the previous embeddings of all the previous tokens. Okay, this would give us some real numbers. Okay, now we want to use these real numbers to collect a weighted sum of the previous embeddings. Now this is a dot product, and the context window can be fairly large. So this is not a fairly well-bounded function. What we would want to do is, because we don't want these embeddings to grow too much, we want them to be bounded. So what we suggested was that we would try to use some sort of weighted sum where the weights add up to 1. Okay. And I asked you guys to give me a function for that. You guys suggested softmax. So what I'm doing now is I'm taking the dot product of the embedding at time t with all the previous embeddings, and I'm taking the softmax of it. So it kind of gives me the importance score of all the previous tokens for my embedding of my token at time t. I have the importance. Now using this importance, I will collect the information from all the previous embeddings. And what we saw was that this is just the softmax of the two embeddings times the embedding value at all the previous times from time 1 to t minus 1. This is a valid attention approach. So this, what we have set up here is that what are some of the limitations that you can think of? Okay, so the first one that I can tell you is that if we use embedding as a mechanism for attention, so essentially I'm using the embedding from time t and taking its dot product with all the previous times, I might at times need to attend to the embedding at time t itself. Okay, this is what we do in attention, is that we don't only attend to the previous tokens, we attend to the token itself as well. Okay, if you are using dot products, then time t will get a fairly large weight because it's dot product of a vector with itself. These would be unreasonably larger compared to the other tokens. This is one drawback. The other drawback is that you can see that I'm using embedding for 3 purposes. I'm using the embedding from time t to collect information from all the other times from 1 to t minus 1. I'm using the embedding from time 1 to t minus 1 to convey or to tell or to see the match with the embedding at time t. And I'm also using these embeddings to pass the values to embedding at time t. So this one vector is stand-in for 3 things. The typical names for them is queries. Query is the question that embedding at time t is asking, or the information that it's trying to collect. Key is the answer which embedding from 1 to time t are providing to query to the query which was launched by embedding at time t, and value, which is the information which was actually passed to the embedding at time t. So one embedding is stand-in for 3 values, which can overload the vector. So typically what we do is we take this embedding vector. So we get an embedding vector, and we get 3 vectors out of it: a query vector, a key vector, and a value vector. Okay. How do we get it? Well, the simplest thing that we know how to do, essentially just a linear transformation. Okay, now this query key value pair for each embedding gives you a much better implementation of attention. So what I will do now is that if I want to attend from time t to all previous times, what I will use is the query at time t, and I will take its dot product with the keys for all the previous times. So key at time 1, key at time 2, key at time t minus 1, and key at time t. So essentially, I will have the dot product of the query at time t with the key at all the previous times. Okay, again, I'll take the softmax because I want the weights to sum up to 1. And then I will multiply it with the value at any corresponding time that I'm interested in. So now, if you want to collect the information from all the previous tokens, essentially you would do is you'll start from t equal to 1, go all the way till t. Okay, this is essentially the attention implementation in state-of-the-art transformers. Okay. You take the embedding vector, you do 3 linear transformations of it, you get a query vector, a key vector, and the information to get t is query empty dot product with keys for all the previous 10 steps, all the way at up till and including t. Softmax of it, multiplied the value vector, multiplied with the value vector at each of the previous time, and you add them up. So now this query, essentially, it would be something like this. So let's take a concrete example. Okay, so let's say this would be the capital of UK is London. Okay, so let's say that we are here, the query at quality minus 1, t minus 1, t minus 2. The query at time t now it has information of London, but it will try to see if what are we talking about currently in the context of London. Are we talking about London as a place of shopping, as a place of business, as a financial capital of the world? What are we talking about? So it would ask, the query would ask like, hey, do you have any modifier for London? Do you have any information which can modify my current understanding of London? So this query will go and it will talk to capital, okay, and it will talk to UK. So capital will pass the information that, hey, I'm currently talking about the capital cities of countries. And UK will pass the information that I'm currently talking about UK. So this query will ask the question, hey, do you have any modifier for me? The key at t minus 2 will tell, hey, yes, I have a modifier for you, which has the information of the country where London is the capital of. And at key at time 2 will tell it that, yes, I have the information, and the information that I have is that I'm currently talking about capitals of countries. This is how query asks a question of all the previous tokens. Key answer that question. Key is yes, no. I have the information, I don't have the information. Of course, it's not a 0, 1. It's a number which is soft between 0 and 1. This can vary. And then value is the information that would be transferred. So this capital information would be relevant to this London. So a weighted version of it would be added here. Okay. UK would be important for this London. So a weighted version of this information would be added here. That's essentially the state-of-the-art implementation of attention in modern architectures. Okay, everybody is with me? Okay, so now a couple of simplifying steps. So we are essentially talking about key query value pair and attention. Okay, I just want to make a little bit of distinction between 2 types of attention, which is self-attention and cross-attention. Okay, so the mechanism that I just showed you, this is called self-attention. Okay, why is it called self-attention? Attention can happen in 2 setups. One is where you are, for example, creating some text. You are doing language modeling. You are generating language. So you have a sequence, for example, capital of UK is London. So this attention that we implemented, where the query at time t was talking to the key at time t minus 1, key at time t minus 2, all the way till key at 1. This is within the same sequence, right? We are just working in English language. It is the same sentence, which is attending to different parts of itself. Okay? This is called self-attention. Okay. What would be cross-attention? For example, when you have two sequences where you have to set up attention between them, for example, language translation. Okay. So how would we say the capital of UK is London in Arabic? عاصمة المملكة المتحدة. It's not very good Arabic, but you get the point. Okay. So now let's say I'm doing language translation. I have Arabic text and I want to write the English version of this. Okay. So I will have attention mechanism in Arabic, where each token of Arabic will talk to each other token of Arabic and collect information from them. Okay. This, by the way, does not even have to be masked. A token can talk to the previous token. It can also talk to the future token. Because I'm doing translation, I have the full Arabic sentence. Okay. So this token will talk to this token. It will talk to this token. It will talk to this token. It will collect information. Okay. Now I'm starting the translation. So I'll start the translation by start of sentence. I will have an embedding for it. Okay. This embedding will talk to the Arabic text. So it will talk to London. It will talk to Muttahida. It will talk to Al-Mamlika. It will talk to Al-Asma. This is called cross-attention. Okay. Now the question that I have for you is, how can an embedding in English language talk to an embedding in Arabic language? Remember the mechanism that we have queries, keys, and values. So what will I use from the English part of the sentence? Query, key, values. Out of these three, what will I use from the English sentence? Query. Okay, because essentially you are collecting information. So the query at time 1 would be like, hey, what is the context? What are we talking about? What is the Arabic sentence about? That would be more or less the query. And the keys and values would come from the Arabic sentence. Okay, so this, for example, Asim al-Mamlika al-Muttahida London, different tokens from it will pass information about the Arabic sentence to the start of sentence token and tell it like, hey, we are talking about UK. We are talking about capitals. We are talking about London. This information would be passed to the embedding at start of sentence. And this embedding then would produce the next word. You will have a distribution. You'll have a function which will take this modified embedding. Okay. And it would produce the next word. And the next word probably would be like the. Okay. Then the embedding of the would talk to all the embeddings of London. By the way, when we create the architecture, these architectures can have layers where you have self-attention and layers where you have cross-attention. Okay. So you have to provide both mechanisms for this. So if you're translating English into Arabic or Arabic into English, you have to have mechanism where English statement is talking to Arabic statement. But you also have to have mechanism where English sentence is talking to itself to see like how much of the sentence it has translated. So you'll have separate layers. Some layers would be self-attention, some layer would be cross-attention. Okay. So this is the two types of attention mechanisms that we have. Okay. Yes. So what our friend is asking is that the self-attention in this translation example, what is it for? Cross-attention, we understand. In translation example, English sentence has to collect information from Arabic sentence. So you have to attend to the Arabic sentence. But why are we using self-attention in this translation example? Self-attention is required because you are also writing this English sentence as you go along, and you need to know how much you have written. Okay. So for example, I'll give you an example. Let's say you started with start of sentence, you created a token the, you created a sentence capital, you created a token of, you created a token UK. Now, UK, the token of UK has to talk to the English sentence as well to see how much of sentence it has written already. So the UK will collect the capital of, and it would say that, okay, I'm currently talking about the capital of UK. Then it will talk to the Arabic sentence and say like, okay, what were we talking about the capital of UK? Okay, was I saying the capital of UK is populous? Why was I saying the capital of UK is a business hub? Was I saying the capital of UK is London? So it would look at the Arabic sentence, and the Arabic sentence would say, no, I was talking about the capital of UK is London. So then that information is connected from the Arabic sentence, and it would do it like this. Yeah. So this language translation is an example where you have both self-attention and cross-attention. Some layers would do self-attention and some layers would do cross-attention. Okay, so now let's look at a concrete example of GPT-3, and let's see how these different things are set up in GPT-3. Attention layer. So GPT-3 is what we call the decoder-only model, which means it doesn't do any cross-attention. It has just self-attention. Okay, so GPT-3. And we looked at it in last week, broadly speaking, the parameter space of GPT-3. Today, we are going to look at some implementation detail, like how these key query value matrices are learned, how these are set up, how multi-head attention is set up, and so on. Okay, so some details about GPT-3. The vocabulary size in GPT-3 is about 50,257 tokens. Okay, and the dimension, the embedding dimension, is 12,228. Okay, so I have a question for you. So you have an embedding for a token, which is 12,228 dimension, and you have to do some linear transformation of it. You have to do a query. You have to do a linear transformation for a key and a linear transformation for a value. The first question is, do you think we need all the 12,228 dimension to do an attention mechanism for an embedding? So think of it like this. A query, how did we set up a query? The query is basically collecting some information about the current embedding, right? So this information would be in terms of question, like, hey, do you have information of capital? Do you have a noun modifier? Do you have a verb modifier or something like that, right? Do we need 12,228 dimension to ask these questions? The answer is no. So we can ask these questions in fairly low dimension space. So that's what we use in WQ, WK, and W value. Okay, so what we do is we say that these matrices are 128 times 12,228. So we are asking these questions in a fairly low dimensional space. By the way, why would I not want to ask this question in high dimensional spaces? It's purely a computational thing. Okay, if you have queries and keys and values in this high dimensional space, then you would have the dot products in this high dimensional space. And dot product basically is of the order of D. If you have a D dimensional vector, you will need D multiplication to do the dot product. If D is 12,228, to do a dot product between two vectors, you will need 12,228 multiplications. If D, the dimension of the embedding, is 128, then you would only need 128 multiplication. Okay, so this is a computational saving step. So our W query, WQ, and W value, all of these are 128 times 12,228 dimension. So we take our query keys and values, we take an embedding in 12,228 dimension and get queries, keys, and values which are smaller. So this is now 128 dimension, 128 dimension, and 128 dimension. So these two I can understand right away why I would want query and key to be in a low dimensional space. Why? Because it's answering a question and providing answer to a question. This eventually would turn out to be a scalar. So a dot product, even if it's in the low dimensional space, doesn't change anything. But how can I have the value in low dimensional space? Because this is what I'm adding to the embedding. I have a 12,228 dimension embedding. I cannot add a 128 dimension vector to it. So can somebody give me some good intuition as to what that might be? Remember, we did it last week. We said that our value vector is 128 dimensional vector. But the question is, we are collecting these weighted sums of these values and adding it to our embedding. But our embedding is 12,228 dimensional. So we cannot add a 128 dimensional vector with a 12,228 dimensional vector. Okay. Okay. So yes, you are going somewhat in the right direction, but the intuition that we use is we say that we have this large space, 12,228 dimension, but the changes that we want to make in this large dimensional space is on a low dimensional manifold. So we have a 128 dimensional space where we want to make changes in this value vector. Okay. So what I'm saying is that I have an embedding at time t. I'm adding some changes into it, right? These changes that I will add is not in the full space of my embedding. It's in a low dimensional space. Okay. So the change that I'm adding, it is of rank 128. So you can write it as a linear combination of 128 vectors. Remember, all of these 128 vectors would be 12,228 dimension. Okay. So this is basically telling you how much of each of these 128 dimension, low dimensional space changes are you adding to your embedding. So of course, we need to have a matrix of which has 128 columns, and each one of these has 12,228 dimensions. Okay, so this value, this represents how much of this I should add to my embedding. Okay, this is the first value here. Okay, similarly, this A128, this would be how much of this change of the 128 dimensional vector I would add to my embedding space. Again, this is done for computational efficiency. Okay. So I took a 12,228 dimensional vector and I create 4 vectors out of them. Okay, well, 3 vectors and 1 matrix. So I create a vector which is 128 dimensional, a key vector which is 128 dimensional, and a value vector which is 128 dimensional. And then I collected a matrix of 128 times 12,228 dimensions. Okay, so these are 128 vectors. Each one of them is of the full dimension as an embedding, and it would take the changes in value and convert it into a corresponding change in the space of the embedding. Okay, so now I have an embedding which is 12,228 dimension. I have a key vector, a query vector, a key vector, and a value vector extracted from it through linear transformations, WQ, WK, and WV. This gives you query key and value. And finally, I have a W output as well, which is the matrix of 128 vectors, each one of them of 12,228 dimensions. That's basically how we implement the attention mechanism. Let me write the full setup for you. Okay, and let me see if we agree on it. So mostly your deep learning libraries would use a row representation of embedding. So embedding would be a row vector. Okay, so you would have an embedding as a row vector. So embedding for token 1, embedding for token 2, embedding for token T. Okay, so let's say I take the GPT 2 example and I have 32,000 context window. Okay, so this E matrix, because it has the context size is 32, it has 32,000 tokens. What would be the size of E? What is the shape of E? So this is token 1, token 2, all the way till token. No, so let's start with rows. How many rows does it have? No. 32,000 rows, okay, and 12,228 columns. Okay, that's your E matrix. Okay. Now my W query matrix has to take this 12,228 dimension and convert it into 128 dimension. So first thing is, where should I multiply WQ? On the left hand side or on the right hand side? On the right hand side. Okay. So you will have E times WQ. And now remember, the number of rows of E's cannot be changed by a linear transformation from the right hand side. So the output of this is 32,000. How many columns do I want for it? 128. Okay. So what would be the shape of WQ? Remember, for this matrix multiplication to be valid, the number of 12,228, the number of rows of W has to be equal to the number of columns of E times 120. Okay. So now this will give me the queries. Okay. How will I get the keys? Again, same transformation, E with WK. Remember, WQ, WK, WE, WO are learned. Okay, all of these are learned. We learn them. I'm sorry? They are same size because you are learning same size vectors. Okay, so this will give you keys. Similarly, embedding with WE will give you values. And finally, you have a W out. I will not mention the size of W out yet. It will become clear in a bit. Just bear with me for a second. Okay. Now let's take the attention score. Let's see how much each token is going to attend to each other token. Okay. So let me take query 1. Okay. And let me take its attention score with, let me write it as a row vector. Let me write it as a column vector. Okay. So if I take the dot product of query 1 with K1, this would give me the score. Okay, I still haven't normalized it. I still haven't done the softmax, but it will tell me how much Q1 should attend to K1. Okay. Then if I do the dot product of Q1 with K2, this will tell me how much Q1 should attend to K2. And I can do it all the way till the final time. In this case, it's 32,000. Okay. But can you tell me something about these operations? Are these operations dependent on each other? They are parallelizable, right? All of these dot products are parallelizable. I don't need to wait for query key dot product at time 1 to create query key dot product at time 2 and time 3 and time 4 and so on. So these are parallelizable. So what I can do is, I'm hoping that you guys will allow me to do it, is that I will take this query 1 at time t, and I will create a matrices of keys. 1, 2, all the way till KT. Okay. Now this is a matrix operation. Okay, so this is a matrix. And I can do it with one matrix operation. So I'll take the query and I'll take its dot product with all the keys, starting from time 1 all the way till time t. Everybody is with me? One matrix operation. Rather than having t dot products, I've combined these t dot products into one matrix operation. Okay. I'm hoping that you guys would allow me to do the same for query at time 2. Okay. Query at time 3. And query at time t. Okay. This matrix would come as is, right? This is just copied, copied, copied. Okay. Now I have a question for you. To take the matrix product of query 1 with key matrix and the matrix product of query vector at time 2 with key matrix, can I do them in parallel? Are these operations parallelizable? Muhammad, are these operations parallelizable? This operation and this operation and this operation, are they dependent on each other, or can I do them independently of each other? They are parallelizable. I can take these matrix product independently of each other, so I can parallelize them. So if you guys will allow me, what I will do is I will collect all the queries in a matrix. So this would be Q1 transpose, Q2 transpose, all the way till QT transpose. Remember, these are like this. Then I have K1, K2, K3, all the way till KT. Okay, and I'll take this matrix product and it will give me the full attention score. Okay, the attention of each query to each key in my context window. So you see now I had 32,000 tokens, but all of this operation I connected them into one matrix operation. Okay, and typically we write this as Q matrix, this as K transpose. Why we write this as Q matrix? Because you see, I did this operation with this is Q. Okay, this is K, and this is Y. Okay. So now, in a very efficient manner, I can combine all these operations. And by the way, that's why transformers are so popular, because they are highly parallelizable. Okay. By the way, are recurrent neural network parallelizable? Can you parallelize them in time? No. Okay, you can't parallelize them in time, because to find the value at time t, you have to collect the history up till time t minus 1, which means you have to go to time 1, time 2, time 3, time 4, time 5, all the way till time t minus 1. So now we see, okay, transformers are very good. Okay. I still have one thing missing. I will make a note of it, which is causality, or looking at the future. So currently what I have done is, if you look at this setup, each of my query can talk to each of my key. Okay, this is not a good idea in language generation. For example, if you are in language generation, if you are creating the 3rd token or the 4th token, it should not be allowed to talk to the 5th or 6th token. Because remember, the original language model that we did, we conditioned the next token on all the previous tokens. Okay, so if you are at a token, its future tokens would depend on this token. So it cannot talk to the future tokens, because it will give them information, unfair advantage about the current token. So you can look at, imagine how we do writing. When we do writing, we are writing it one word at a time. So you are allowed to look at all the previous words that you have written, but you're not allowed to look at the future, at the words that you haven't written yet. You cannot attend to them. This mechanism, which I have currently drawn on my board, it talks to the future, but we'll fix it. Just bear with me a little bit, okay? So far, we have the raw attention scores from each query to each key, okay? Remember, we wanted them to be weighted up to 1, the sum of these weights to be 1. So how can we do that? We'll do a softmax. Okay, I will add one more thing here. This is just for numerical stability. I will explain what this is. It's just a factor, okay? Square root of the dimension of your vectors. Okay, let me see if I can ask you one more question. So which dimension am I taking the softmax on? Am I taking softmax along the rows or softmax along the columns? You are taking softmax along the rows, okay? Why? Because you see, take a query and attend it to all the keys, and then the sum of a query, the sum of the weights of a query attending to all the keys have to be 1. These are in along the rows, so you will take the softmax along the rows. Okay. Okay, so this is done. Okay, now I have to take this. Essentially, what would come out of this is a matrix, which is called an attention matrix. Which tells you how much of each token is attending to each token. It's this Q1, Q2, all the way to Qt, and Q1, Q2, Q3, all the way to Q2. What is the size of this matrix, by the way, in this particular context? Remember the context window, we took it to be 32,000 size. So what would be the size of this matrix? 32,000 by 32,000. Okay, you have 32,000 rows and 32,000 columns. This is 32,000 by 32,000. And now you have a value here, which tells you how much each token is talking to all of the previous tokens. Okay. And the sum is the sum along column 1 or the sum along row 1? In fact, in my notation, let me transpose it. No, just give me 1 second. Because the notation that I have used, I have queries along the rows. So I have to reformulate it slightly. Okay. So the sum along the rows would be equal to 1. Okay. This would sum up to 1 because this is the direction along which you are taking the softmax. Okay. Can you tell me something about this sum? How much would this sum be? Okay, we don't know the exact values, but we can give some bounds on it. No. Exactly. So the lower bound is 0. It's positive. It cannot be negative because all the numbers are positive. And it's upper bounded by 32,000 because maximum value in each of these cells is 1. So I know I have some bounds on it, but I don't know the exact sum of it. Okay. Anyways, so now the attention mechanism is done. Okay. Now I have to take these attention scores and collect the relative change in embedding of all of this 128 low dimensional space. Okay. So let me call this attention. Okay. Attention matrix, AWT. Okay. So I have to take this attention matrix. I have to do some operation on it to give me the sum of the change in this low 128 dimensional space. So how would I do it? I have a value matrix. Remember, what is the size of the value matrix? The size of the value matrix is 32,000 by 128. Okay. So the size of attention matrix is 32,000 times 32,000. So it seems natural to multiply it with weight. Okay. So this is 32,000 times 128. Okay. And the output size would be 32,000 times 128. So now you have for each token, the embedding change in this 128 low dimensional space in your larger 12,228 dimensional embedding space. But can somebody explain a little bit to me, what is this doing? What is this matrix multiplication doing? Okay. So this matrix multiplication is, somebody wants to take a stab at it? Yes.
There's like extracting the relationship between the two tokens. So
Yeah, this is done here. So the relationships are done here. All the relationships are calculated in the attention matrix. You have them here.
yeah, the importance between them.
Yes.
So this one, extract the importance between them.
Yeah, this is all done. It's all here. I'm asking about this thing. What is this thing?
Extracting the importance in lower dimension.
Yes, yes. So essentially what it's doing is, remember you have this 128 dimensional vector for each of the token, which is telling you which low dimensional space this particular token is changing the embedding in. Okay, you essentially go to each token, multiply the change of this low dimensional, multiply the low dimensional vectors with the corresponding importance with it, and then add it for all of these. So essentially, let me just do a simple simulation of it. So let me take a 3x3 example. So let's say I have 3 tokens. Okay, let's say I have a attention matrix for this 3x3. Okay, so this is Q1, Q2, Q3, K1, K2, K3. Let me write this as an example. Okay, and let me put some numbers. So let's say 0.1, 0.4, 0.5. Okay, now let me create the value vector. Let's say the value vector V1 was, let's say these are 4-dimensional vectors. Okay, so 1, 0, 1, 1. Okay, value vector at time t was 2, 0, minus 1, 0. And value vector at time 3 was minus 1, 0, 1, 0. Okay, so what this will do is it will take this one, multiply it with 0.1. I'm just looking at this one for the first token. Okay, it will take this one, multiply it with 0.4. It will take this one and multiply it with 0.5. So this is not dimension of Q and K. This is dimension of attention. Q and K were 4-dimension vectors. You take its dot product and you put it there. Okay, this is context size. So the context size is 3. D is, let's say, 12,228. But I am working in an embedding dimension. The key, query, and value are 4-dimensional. Okay. Now what I should do is I should write them as transpose, V2 transpose and V3 transpose. Because remember, I'm writing them as vector. So you will take this weighted sum of them and you will get the output vector. Let's say the output vector is, let me do the addition. Okay, so it's 0.1, 0.8, and minus 0.5. So this is 0.3. Okay, then this is 0, 0, and 0. Okay, then this is 0.1, minus 0.3, and 0.2. And this is 0.1 and 0. So this is the output change that is going to be implemented in the embedding of the first token. I've just done the dot product of the first row of my attention with the V matrix. I will do it for the second row. I'll do it for the third row. And this basically will give me a matrix which will tell me how much I have to change my embedding in this 4-dimensional space, which is a subspace of 12,228 dimensional space. Everybody is with me? Any question, guys? Okay. Okay. So now this is done. I have, for each of my token, I have the change in this 128 dimensional space. Now I have to project this 128 dimensional change back into my original space. Okay. And for that, I would need a W out matrix, which would have 128 rows and 12,228 columns. Essentially, this W out matrix would tell me in my 12,228 dimensional space, which is this low dimensional space that I want to make changes in. Okay, so now I was here, I have attention matrix multiplied with V, which is giving me the change in 128 dimensional space. I would multiply it with W out, which would take this 128 dimensional change and project it back into 12,228 dimensional space. So now what is the output dimension of this? 32,000 times 12,228. And if you look at it, this was the size of my original embedding as well. So you can add this change onto the embedding. So an attention layer was just going to take an input embedding, create a change for it, add it to the embedding, and that's basically transformation. Okay, that's why it's called transformers. Just transforms an embedding into an embedding which is richer by collecting information from all the tokens in the context. Everybody's with me? Okay, so now I'm going to take one next natural step. Remember, a token might not be interested in just one type of change from its previous token. For example, a particular query would be for a token might be, okay, do you have a word modifier? This is the query. Okay, you might want another query, which is like here, are you part of a compound sentence? You might have another query, which is like here, do you have any noun in the context? You might have another query. So we cannot rely on learning just one type of query. We need to have the ability to have multiple queries in our attention mechanism. That's where we created multi-headed attention. Okay, so multi-headed attention is essentially we had an embedding. Okay. So we had a WQ, a WQ, a WV, and a W out. And from this we got query, key, value, and out dimension. Okay, but this is one set of query, keys, values, output. Okay, we want the ability to learn multiple of these. Okay, for example, one query would be asked one type of question, another query would be asking another question, another query would be asking another question, and so on. So this, we would call it the first head of our attention. We can very similarly use another set of WQ, W key, WV, and W out. Okay. This is the second head. This would give you the second query, a second key, a second value, and a second output. And you can have many of these. Okay. Now you can see another good intuition for why we wanted to take this embedding and do it in a low dimension space. Because we want these low dimension space to ask specific questions. And specific questions do not need to be asked in a high dimensional space, because I wanted to have the ability to have multiple heads. Each head would ask one specific type of question. And you will have multiple heads, which will ask multiple of these questions. So previously, if you look at all the numerical computation that I did, I had a query matrix. I took its transpose, its multiplication with transpose of the key matrix. I take the soft max of it. I multiplied it with the value matrix, and I multiply it with the output matrix. This is for one head. Okay. Let me just on the side do how many weights are there in this one attention layer. So we have 4 matrices, or matrices are of the same size, so I can just, I'm counting their parameters. And each one of them is 12,228 times 128. So this is the number of parameters for a single head of attention for a single layer. In GPT-3, we have 96 headed attention. Okay, so you would have this whole thing times 96. If somebody can do this calculation, I think roughly, I just want a rough number for it. But the question is, I can do this operation, the full attention for a single head. How would I do it for multiple heads? Well, one obvious thing is that you can just write a for loop and go to all the heads and do all the calculation for all the heads. Okay. But can I do something better? Can I parallelize it? Can I do it in a way which is slightly more well posed and slightly well structured? The answer is yes. And I'm going to give you an idea for it. And let's see if you guys agree with me or not. So, yes. Okay, that's a very good question. So the question that our friend is asking is, what is the change from head 1 to head 2? Everything is the same. What is changing? What is changing are these weights. Okay, the weights that you are learning, these are changing. And by the change of these weights, the query key pair would respond to a different type of information. No. We initialize randomly. Weights are initialized randomly. Okay. This is one of the fundamental principles of machine learning. Weights have to be randomly initialized. You cannot do, so you will never see a machine learning algorithm initialized with zeros. It would not work. It would not be trained. You have to initialize them randomly. Okay. So let's come back a second and let's look at the dimension of our query matrix. So our query matrix was 32,000 times 128, right? What I'm going to do is I'm going to propose that what we do is and now we have multi-headed attention. So for each head, I would represent a superscript to number the index of the head. Okay, so Q super 1 would be the first head, Q super 2 would be the query of the second head, Q super 3 would be the query of the third head, and so on. So the first thing that I'm going to propose that we do is we collect all the queries in a single matrix. So Q1, Q2, Q3, all the way till Q96. Can I do that? Yes, I can do that. Okay, all of them have the same number of rows, so I can concatenate that. Okay, so what would be the shape of this matrix now? Start with rows. How many rows? 32,000. How many columns? 96 times 128. Okay. Now remember, what do I want? I want the matrix multiplication of Q1 with Q1 transpose. I want the matrix multiplication of Q2 with Q2 transpose. I want the matrix multiplication of Q3 with K3 transpose. How can I do that? I want to create a matrix of keys such that the output gives me this. Put them in a column. Sure. Okay. So let me do that. Okay, so what our friend is saying is, let's do this. Let's do K1 transpose, K2 transpose, K3 transpose, all the way till K96 transpose. When I do that, you will see that this would not be this. It would be this. And I don't want that, because then it's not multi-headed. I don't want to add the outputs. I want to keep each one of them separately. Okay, so this would not work. Yeah, because it has this addition and I don't want to add. Okay, so I can give you a hint. Think diagonal matrices. Think diagonal matrices. Okay, so if I have a diagonal matrix where I have K1 transpose here, K2 transpose here, K3 transpose here, all the way till K96 transpose here. Let's just ensure that this matrix multiplication is valid first, then we'll go. Okay, so K, by the way, the shape of K is all KIs is 32,000 times 128. So if I take the transpose of it, each one of these is 128 rows, right? And each one of these has 32,000 columns. Okay, I do this matrix multiplication. What will I get? I will get Q1, K1 transpose, dot product of this row with the first column, then Q2, K2 transpose, dot product of the row with the second column, then Q3, K3 transpose, dot product of the row with the third column, all the way till Q96, K96 transpose. What would be the shape of this? The rows would be 32,000 and the columns would be 32,000 times 96. Okay, I seem to be going somewhere. I have attention map. This is the attention map of the first head, attention map of the second head, attention map of the third head, attention map of the 96th head. Okay, I will do the appropriate. Let me call this attention tilde. Okay, so I take this. It's not attention tilde yet. Let me do the softmax and then call it attention tilde. So I'll take the softmax of it and I'll call it attention tilde. Okay, of course, I have this normalization with D, but I'll keep it on the side. So you got attention tilde, which is 32,000 times 32,000 times 96. Okay, you have the attention score for each of the attention heads. Now you have to multiply it with the V matrix. Okay, again, think diagonal matrices. Okay, so you take this attention matrix, we multiply it with V matrix, but now I have to have V1 here, V2 here, all the way till V96 here. Okay, what was the shape of V matrix? V matrix was 32,000 times 128. Okay, I have 96 of these. Yeah, so you have 32,000, 32,000, 32,000. Okay, 128, 128, 128. So the size of this is 32,000 times 96 by 128 by 96. So the matrix multiplication would be 32,000 times 96 times 96 times 128. So this dimension cancel out, the inner dimension of the matrices goes out, and you get 32,000 times 128 times 96. Yeah, let me call this attention V tilde. So you take attention V tilde and you multiply it with W out 1, W out 2, all the way till W out 96. Okay, what was the shape of W out? The shape of W out was 128 times 12,228. So this would become 12,228 times 128 times 96. The shape of attention V was 32,000 times 128 times 96. Inner dimension would go out. You would get 32,000 times 12,228, which is the shape of the embedding. So this essentially represents just the delta E. Okay. So essentially all of it, we are doing it in a single set of matrix operations. Okay. So very elegant way of handling multi-headed attention. Why, by the way, this matrix mechanism is good rather than doing a for loop or something like that? Because all of it is parallelizable. Okay. If you can parallelize it, you can do it really, really, really fast. And that's what has made transformers so popular. So now we know essentially all the components of a transformer. All the components of a transformer are essentially just two components. It is multi-headed attention and a feed forward. So we have done the multi-headed attention. Let me write it mathematically as well, so that we know what we are talking about. So I would say that the output embedding for a token at time t is the input embedding for a token at time t. Okay, let me just write out and in, plus summation from h equal to 1 to h, which means going over all the heads, summation from t equal to 1 to t, which means going over all the history, okay, and collecting delta E which is imposed at input by token t at head h. Okay. So essentially, the embedding of each token in each head is creating a small change for the output embedding, and you are just collecting it. You are adding all of it up. Okay. Now, a question that I'm going to ask you is that why did I do it like this? Why didn't I do it like this? Which, by the way, also I can do. Going over all the heads, going over all the tokens, and just creating or collecting the change in embedding. Why is 1 better than 2? From a machine learning point of view, both of them are the same. Both of them have the same number of weights. Of course, you're learning slightly different things, but the learning capacity for both the networks are the same. Okay, but 1 is significantly better than 2. Can somebody tell me why? Okay, yes, it's because of the skip connection. Because of this skip connection, adding input directly to the output, the gradients become slightly well defined. So even if you're getting, for example, vanishing gradient for this component, you have a gradient for this, which is 1. Yeah. So you can have fairly deep networks. It makes learning significantly easier. Okay. Nothing changes in terms of like the network architecture other than just a skip connection. You add input to the output. That's it. Okay. But this small trick makes training deep neural networks and deep transformers significantly easier. Okay. So, okay, we have done an attention layer. One thing that you might have noticed is that there is no non-linearity in attention layer. Okay. So other than, of course, the softmax. Okay. Where do the non-linearity comes in transformers? It comes from the fully connected layers. Okay. So essentially what has happened so far is that you have some input embedding for a token. And then you have multiple changes. This is, for example, change from token 1 in head 1. Okay. This is maybe change from token 1 in head 2, all the way till token T in head H, and so on. So all these things are added. And one of the things that you might note is that the information flow is component-wise, because these are vector addition. Each component is added to the corresponding index. Okay? There isn't much information flow across different components, which is not necessarily a good thing, because different components of your embedding might want to convey some information to other embeddings as well. And this is done with the fully connected layers of transformers. So how do these work? After your attention layer, so you have an embedding in. After your attention layer, you get an embedding out. Okay. Now this is a vector. What you would do is you will have a neural network. Typically, this is a two-layer neural network, which will take each of these components as an input. Okay, do some operation on it, fully connected operation on it, and output an embedding of the same size. I will zoom into this operation to show you this in a little bit of details. So essentially what would happen is that you will get embedding as input, and now you will have some hidden units of your neural network. Okay, you will take the first component of the embedding, multiply it to the weight. Each solid line is a matrix multiplication. The weight is learned. So now you can see that all the components are sharing some information into one hidden node. Similarly, let me take a different color. All the components are collecting some information in a hidden unit. Similarly, all the components of the embedding are collecting some information in a hidden unit. So this allows different components to talk to each other. Okay. Of course, because we want to keep the embedding dimension same. So the output component of this neural network will also have the same number of components as the input embedding. But this neural network essentially serves to allow for mixing of the different components of the embedding vector. Okay. And then at the end of this MLP, you have, of course, some non-linearity. The non-linear layers that we typically use is some version of Swigglue or Swish or something like that. Let me just briefly explain what these non-linearities are. So the best non-linearity that we had for convolutional neural networks was ReLUs. Okay. Why were ReLUs good? Because ReLUs have good gradients. Okay. The major improvement that we have had in NLP on top of this is basically a modification of ReLU, which is essentially sigmoid of x times x. Okay. So what happens is, what is a sigmoid? Sigmoid is essentially 1 when x is bigger. Okay, and it's, sorry. So sigmoid is essentially 1 when x is big, and then it's essentially 0 when x is small. If you do this, you would see that this would essentially turn out to be something like this, but then a little bit something like this. Okay, and that's what makes slightly better. We don't have very good theoretical proofs as to why this is better, but it essentially in practice works better. Okay, and then people have done slightly better version of this where they have some weighted components of these. Okay, but essentially the core idea is this. So rather than going for simple ReLU, do some sort of product of sigmoids or weighted sigmoids with some linear functions. Okay, so we have a whole range of these. We have Swish, which is essentially this. Okay, then if the sigmoid can be weighted, if the beta in this is 1, it's called CLU and so on. I will try to create a small PDF of it and share it with you so then. But essentially, this is the idea. Okay. So these are the non-linearities in these layers, and that's essentially it. That's the full architecture of transformers. Okay, and the relative changes from, let's say, this, by the way, I'm talking about GPT-3. So GPT-3, the newer versions of GPT have come. Llama was an improvement on architecture. Mistral had some improvements on architecture, but these improvements on architecture are marginal. The core idea is essentially the same. So what you will have is in your large language models, essentially you would have an embedding layer, which will take vocabulary and convert it into embeddings. Okay. So this would be, what am I doing? I need a column vector out of it. Okay. You will have embedding for the first word of the vocabulary, embedding for the second word of the vocabulary, all the way till embedding for the last word of the vocabulary. Okay. In the case of GPT-3, what would be the size of this? So we have 12,228 columns, and we have 50,257 rows. I think it's about 516 million parameters. This is the embedding layer. Then you have the attention layers. Attention layers, I will call it, because these are multi-head attention layers, I'll put in a note for it. So multi-head attention layers, remember we had, in each layer we had 4 weights, weight matrices. Each one of these is 12,228 times 128. Then we have 96 headed attention, and I think we have 96 such layers. Okay, so if you do it, that would be roughly of the order of 50 billion parameters. Okay, similarly, for each layer, we have MLP, the multi-layer perceptron, okay, which is, remember we had one hidden layer network, so it has 2 layers. The 2 layers are symmetric. So this is 12,228 times 49,152. This is the number of weights in the layer. We have 2 of them, and then we have 96 layers. Okay, and if you do it, that would be of the order of roughly 110 billion. This is, I think, of the order of 55 billion. And then we have one output layer. Output layer has to take the embedding. After all the calculations you have done on the embedding, you have to use this embedding to predict the next token. So you have to have a linear layer which takes the embedding dimension and gives you output distribution on the vocabulary size. So it would be 12,228 dimension times 50 times 257. And this is again 566 million parameters. So if you add this up, this is roughly equal to the 175 billion parameters for GPT-3. Yeah. Yes. You can increase the attention layers, and essentially I'll give you a summary of like what is the overall learning that we have done in large language models so far. So the summary is this: architectures typically are less important. Okay, so for example, thinking like whether let's say 96 layers with smaller number of parameters would be better than 100 layers with larger number of parameters. These type of questions are relatively less important in large language models. What is more important is the overall learning capacity. 200 billion parameter network would be better than 100 billion parameter network. Okay, 100 billion parameter network would be better than a 50 billion parameter network, and so on. These are the general outcomes. So if you are designing an architecture, don't spend too much time on these architectural details. So if you look at it, it's just essentially one attention and MLP layer, just copied 96 times. Okay, so that's what you should do as well. Okay, so maybe use slightly more heads. Okay, maybe use slightly denser MLP layers. This type of small architectural choice. Don't spend too much time on the architectural designs of things. Spend more time on training larger networks. Networks with larger parameters typically would perform much better. Yes. Oh, okay, okay. So our colleague is asking, can I explain the attention layer dimension? And the answer is yes, I can. So what is the attention layer for us? So in GPT-3, we have multi-headed attention, okay, with 96 heads. Okay, each of the head has a WQ, a WK, a WV, and a W out. Okay, and each one of them is 12,228 times 128. This is the number of parameters in them. Okay, each one of them. Okay, each of the four matrices is like this. So let me find out how many parameters are in WQ. The parameters in WQ are 12,228 times 128. Same is the number in WK, same is the number in WV, same is the number in W out. So I have four of these. Okay. Then I have 96 heads. So I will multiply it with 96. Then I have 96 layers of these multi-headed. This is one layer of multi-head attention. I have 96 such layers. No. So this is what I'll do. So your architecture is like this. You have an embedding layer. Then you have a multi-head attention layer, which is essentially this part. Okay. Okay. Then you have a fully connected layer. Okay. Multi-layer perceptron. Then you have another multi-head attention layer. Okay. Multi-head attention layer 1, multi-head attention layer 2. You have all the way till multi-head attention 96. You have 96 such layers. Okay. So you will multiply it with another 96. That's basically the full GPT. And it's a very simple architecture if you think about it. Okay. Nothing too fancy, very simple setup, but works really, really well. Why? Because the parameter space is very large. And attention is a very strong mechanism for collecting information, in context information. Okay. Any questions so far? Nothing? Everything is good? Because I know it very well. but if for example, you guys want to see Llama, so for example, Llama is very similar. The only thing which changes is in Llama, the positional embedding is slightly different. Okay, the RMS part is slightly different, and there is one more change. So rotary embedding, RMS, there is one more change. I'll bring it tomorrow. Mistral, for example, is significantly different because Mistral, rather this MLP part, this is not one MLP part in it. They have multiple, they have 8 MLP parts in it, and they use something called a mixture of experts, which is a good architecture, which I will explain. Okay, so it's good to know that change. But other than that, there isn't lots of architectural change. As I mentioned, architectural changes are not super important. Yeah, what is important is how big your network is. How many parameters you have? Yes. So now we are in, I think with GPT-4, 4.5, and 5, I think we are in a trillion parameter space. So this GPT-3 was 175 billion. And GPT-2 was like 1.5 billion. So it literally like the big change that came with GPT-3 was because of its space. It was massive. Then that allowed us to do amazing things with it. Yeah. This is 100%. There is no. So I'll give you an example. The example for this is that the model size is the engine on the car. Okay. So if you have a better engine, of course, you are in a better car, but the data is the driver. So you can have the best car in the world, but if you put me in it, it's not going more than 60. Okay. So you have to have a good driver in it as well. So you have to have good data. So data is what drives the models. And most certainly, most definitely, high quality data will almost always yield better result. Okay, and as you mentioned that now people are looking at generating better and better qualities of data. Okay, so what I'm going to do is I'm going to give you guys like 5 minutes, and then I'm going to just talk a little bit about, okay, we have an architecture of GPT-3. How is it trained? Okay, because of course, training is an important step. How is it trained? So we'll talk a little bit about it. Let's take 5 minutes. I'm not going to take more than 15 minutes for it because it's fairly simple. The most important component of that for us, which we have not studied yet, is reinforcement learning with human feedback. And I'm going to spend the next 2 days on it. But I just want to motivate the full cycle. So these large language models are trained typically in 3 stages. I want to explain all of these 3 stages, but let's take a 5 minutes break. Okay. So let's get together at 2:15, and if you gather at 2:15, then inshallah I'll let you guys go at 2:30. Okay, so more motivation for you to come on time. Okay, guys, let's settle down. Yes. Yes.
I have some so what we do is part of this is sharing. I'm not going to make it. You can look at it. Now this is exactly, but like slightly. Now we are it's not going to if you like, don't.
Okay, guys, so let's settle down. So tomorrow we'll come, Joma, we go together, come back and resume. Okay, one of you will give me a lift to the mosque and I will come back.
It will be, I think, 40 minutes before.
It's good. I have a small session for 40 minutes. I'll finish it. And then I have planned a few topics which I missed today. We'll do it tomorrow. First 40 minutes. Then when we come back, we'll do reinforcement learning with human feedback. No, believe me, it's good. Breaking it down into sessions is good. It's Ramadan. So it's good to break it. Believe me, trust me. Halas, guys, let's settle down. Let's look at this last part of today's lecture before we say goodbye for the night. Okay, so training of transformers for language modeling. Okay, training transformers for language modeling. Okay, it's typically it's 3-stage process. Okay, stage 1, which is the most important one, the most time-consuming one, and the most resource-heavy, is pre-training. Pre-training of large language models. Okay, pre-training is essentially you take text from the internet and train it to do the next token prediction. Okay, essentially it's modern large language models essentially trained on the entire data on the internet. You take all the publicly available English text data, you give it to the model and train it for next token prediction. Okay, so the goal is to learn language. Okay, just simple language modeling. Okay, not task specification, raw data from the internet, trained on next token prediction, done at very large scale. Okay, this is pre-training. The next step is supervised fine-tuning. Supervised fine-tuning. Okay, this is basically giving the network relatively a small amount, like maybe 5%, 10% of the pre-trained data, but high quality data. For example, let's say we are training GPT-3, we'll do pre-training, okay? Then we take the pre-trained model and we give it high quality data. For example, high quality data, right? Like write a poem on NLP, and we will give it a poem, okay? Ask a question, answer a question based on this paragraph, and we'll give it the answer, okay? Or conversational data, but high quality data, okay? This is the second part of training large language model. Sorry. Okay, second part of training large language model. Essentially, the intuition is that the pre-training, learning to speak the language, goes a long way in training the model for other tasks. Okay, so you don't need huge amount of data to ask your network to do conversations or to be a chatbot. If it learns how to speak English, asking it to become a chatbot is a relatively easier task. Okay, but this is done with supervised fine-tuning. Supervised fine-tuning because you don't change parameters too much, you make minor changes. Supervised because you provide high quality supervised data. Okay, again, it's done with next token prediction, but the data is not just some random data. The data is some high quality data. Yes.
Fine-tuning is to predict the next one.
Yes. Next token, yes. Okay, this entire setup is just for decoder. It's decoder only setup because it's language modeling, which we don't have any encoder. Same architecture, but the first stage of training is just ability to speak a language, so raw training. Then supervised fine-tuning with high quality data, specific tasks. Let's say if you want to train it to be a chatbot, then you will get chats data. Okay, high quality data, you train it fine-tuning for that. And then the last step, which is left, which is the most important part of this current iteration of large language model. This is reinforcement learning with human feedback, RLHF. Reinforcement learning with human feedback. And the idea of this is to have a reward function for the model, where the model can, using that reward function, model can learn to produce better quality data. Okay. Of course, this requires the knowledge of reinforcement learning, which we will do a little bit. But this essentially is the most important component. And I'll tell you why this is an important component. So supervised fine-tuning, you will find good data of what you want the model to do. Okay, you can find that data. That's what we do with supervised fine-tuning. But a very important component in large language models, in language modeling, is asking the model not to do things which you don't want them to do. So for example, let's say you can give network a data of write a good joke, and you can do that. But it would be very difficult to sample all the types of jokes which you don't want your models to do. Okay, or sample all the type of data which you don't want your model to produce. Okay, so to do that, what we do is we train something called a reward model. Reward model will take in some text and it will give it some reward. Okay, let's say from 0 to 1. 1 would mean that this is good output, 0 would mean it's bad output. So the network would produce text in a hope of trying to optimize this reward to get more and more reward. Okay, if we have this reward function, then essentially we are set. Our job is done. We can just ask the network to produce text, optimize the reward for it. Whenever the reward is high, give that text as an output. If the reward is low, don't produce that text. Typically, training the reward model is not a trivially easy task to do. It's a difficult problem. And there is a whole range of algorithms that we use. So for example, we use PPO, proximal policy optimization. We use DPO, direct policy optimization, and now GDPO or GPO. This is the very recent iteration of it, which was popularized by DeepSeek, version 3. Okay, so we will look at what these quote unquote state of the art improvements are. What did they change in this? I have not looked at this yet, but from what I understand, it's a simple improvement on PPO. Okay, the question is, of course, in order to say which texts are better, which texts are not, you would require at least some supervised data to train the reward model. And that's why you might have noticed that when you're using Gemini or GPT, sometimes they give you 2 answers and ask you which one is better. Have you seen that? This is for them to collect data for reinforcement learning with human feedback. Because you need to be able to tell that this answer should get a higher reward. This answer should get a lower reward. And what defines the reward is whether we like it or not. So they are collecting data from you when they are doing that. Okay? Okay.
System block, and then we have
no, generally usually it's this. So why we are using this system? Okay, so what Shah is saying is that when you do fine-tune these language models, you typically would have a system prompt, then user prompt, then something ahead of it. Why is this? So essentially, this prompt is used for zero-shot learning. So essentially, you would ask your network to do something, right? You would ask it to be a chatbot, or you would ask it to be a text summarizer, or you would ask it to be a question answering thing. Now, when you were doing the training, the pre-training, your network had no idea what it was doing. But when you're doing the fine-tuning, basically, this prompt is used to tell the network that, hey, when this type of prompt is given, then you need to do this type of operation. So that's why the system prompt and user prompt are important. So this is basically what we call it zero-shot learning. Okay, so you have a language model, but you have not trained it to do, let's say, poetry explicitly. Implicitly, you have done because you have given it all the data. But how do you force it to just do poetry? By prompt. So when you prompt it, the system prompt and user prompt, then it tells it that, hey, at this particular time, in this particular context, this operation is required of me. So prompting is important. You have to, that's why prompt engineering is it's a whole area. You can do it, but then it would not be fine tuning, you would be training. Because that's what it's trained to do, and now you are fine tuning on top of it. You are training the existing setup and doing something on top of it. You are, of course, allowed to do something without prompt or creating like your own system prompt in this, but then you would have to do quite a lot of training. So if you want to use the learned ability of the language model, then you have to kind of use the system prompt. User prompt, you can, of course, adjust for a particular task and then fine tune for that. Okay. It's very effective, yes. And that's rather surprising that the ability to predict just the next word from the previous word can produce something so conflict. Okay. But anyways, this is essentially the entire set of topics that we wanted to cover for today. So I missed a few topics for today. I'll cover it, as I mentioned, the first 40 minutes for tomorrow. When you go for Joma, when we come back, we'll look at reinforcement learning for human feedback. Okay, 9:45 tonight, inshallah, we'll have the online session. I would very highly recommend that you join it, but it's not mandatory. If you don't join, it's fine. We'll give you a recording, but attend it because it will allow you to ask questions and get some feedback on your work and so on. No, because I need the first 40 minutes for finishing a few topics for today. No. I'll tell you why. So the thing is, it would be very difficult to get everyone to agree on a change. So let's keep it this way. It will be very, I know that there will be one guy or two guys that say, no, I like this one. So it's fine. We come here, we do 30, 40 minutes, then we do Joma and we come back. Okay. No. I know. I just need 30, 40 minutes to finish a few topics. We'll go together. We'll do Jama. We'll come back and we'll open new topic. I have planned accordingly. Like I know that there is little time before, so I have planned accordingly.